Good early, late morning, everyone. I'm Brian Campbell. We're going to talk about token binding today. I was told to introduce myself, so that's probably all there's going to be. I want to thank everybody for coming. I think we're actually running into lunch here. They scheduled this one in conjunction with lunch, so I appreciate you coming out to see me instead of going to get the early lunch. So with that, let's get started. I got a lot of content to cover. I'm going to talk fast, but it probably seems slow compared to Justin talking before me, so makes it a little bit easier. Get started. So the first question is, who am I? I'm going to start out with a little frequently asked questions here instead of a normal introduction. So who am I? Like I said, I'm Brian Campbell. I'm a distinguished engineer at Ping Identity. It's a fancy sounding title, but I think they just gave it to me for having been around a long time. I've been there about 14 years, and they ran out of things to call me, so I got that. And I am the unofficial photographer of Identiverse, formerly CIS. The next question might be that. What, really? Photographer? I thought you were here for tech. Yes, I do photography. Since about 2011, I've been pretending to have another career here as a photographer. I take pictures in a variety of settings, but particularly at Identiverse and CIS. This is a boot camp from a few years ago, so I'll plug this as well to invite everybody to come out to boot camp tomorrow morning at 6 a.m. It's a good time, as you can see from the pictures there. Everybody's having a great bit of fun. So I use these photos, I put them in a lot of my presentations. I do it under the guise of having it be a way to avoid copyright infringement and being a good citizen, but really it's just an excuse for me to put photos in my presentations and make you all look at them. So do I have any actual credentials to stand in front of you to talk about token binding? And in fact, I do. This is one of the token binding specifications in the IETF. And you can see here near the very end in the acknowledgements, on the very last page, I am listed prominently before and others. So I'm the real deal. Some of you might also be asking, didn't I do this talk last year? And the answer is yes. Although I changed a few slides, it's mildly different to change it up. But the sad truth of the matter is new standards take a long time to develop. And so not a lot of things have changed, but we're still in the development process and we're moving forward with things. But it's still a relevant topic. It's still something that I think is really interesting. I'm excited about, but it's taking a little bit of time to progress. So I get the opportunity to talk about basically the same topic as last year, which was actually nice because it meant a lot of less prep work. So can we just get on with it already? But I got to show you one more picture before we get going. And this is Buenos Aires, where one of the IETF meetings was held, where I really got sort of re-engaged with the process of token binding. It was introduced, I was interested in it, but going to this meeting, I sort of reopened my eyes to the potential of it and my interest in wanting to implement it. So I want to start with, what is a bearer token? And a bearer token is, in contrast to token binding, which we'll talk about here in a bit, a bearer token is a security token, any kind of token, that has this property that any person in possession or any party in possession of that token, i.e. the bearer, can use the token for the associated protected resource access. All you have to do is show up and present it, and it's good enough to get you in. No other proof mechanism is needed beyond just having it, and that's a bearer token. It turns out, sorry, wrong slide. And the problem with bearer tokens, here's a real world example. Here are three three passes from RSA. Two of these are real from my actual career. One of them sort of signifies my pretend career or my aspirational career. I got two of these legit. One of them I came about through maybe some more nefarious means, but there's really no way to differentiate between them. And bearer tokens in the physical world, but they're also everywhere online. We use them all the time. OAuth tokens, at least the vast majority of OAuth tokens are bearer tokens. SAML tokens, OpenID Connect, they're all bearer tokens. And cookies, the things that typically are used to maintain and establish your session on just about every web service or online service we use are maintained by cookies, which in turn are bearer tokens. A lot's been done to try to protect them, keep them from being stolen, and for the most part this stuff works pretty well. But if a cookie's exfiltrated or stolen in any way, they can be used by the attacker without any other kind of protections in place. So while there are protections against stealing them, it still happens. Even as late as last year, there was a subdomain takeover attack in Uber where they stole site-wide cookies and were able to bypass their authentication mechanisms based on that. So token binding is maybe a different approach to protecting these credentials than has been previously taken. A lot of work's been done to keep them from being stolen, but you can think of token binding rather as a means to sort of inoculate a token against reuse if in fact it is stolen. So even if it's stolen or lost, an attacker can't use it without demonstrating proof of some other credential in order to use it, and makes it a stronger mechanism. So the token binding working group was formed in the IETF. This happened in Dallas, another opportunity for me to show a picture for you here. And up in the top is the actual working group. So there's a little bit of a contrast between what looks like sort of the glamorous life of standards development when I take my photos around the world and the actual part of standards development, which is a bunch of nerds in a room, not unlike this one. But token binding was introduced, it's a working group, an IETF working group set of specifications that's being developed there and is on its way, hopefully, to being ratified as standard soon. And it's sort of an interesting name because it's token binding is used to bind tokens. And we'll talk a little bit more about how that's done. But by itself, it doesn't actually do the binding. So a quick overview of what it is. I'll get into the details of each of these things as we go, but it's enabling a long-lived binding of cookies or other security tokens to a key, a public-private key pair that's generated on a client or a browser. The use of token binding is negotiated between the client and the server during the TLS handshake using a TLS extension. And then possession of that key is proven by signing the EKM, which is the TLS exported keying material. You can sort of think of it as a cryptographically unique reference to the particular TLS connection in question. And that unique identifier for the TLS session is signed by that key, and that data is sent in every request as an HTTP header. And that proves possession of the corresponding private key associated with the key that's being sent. Cookies and other tokens can then be bound to that key, thus preventing them from being, well, thank you, from being used by someone that doesn't possess the corresponding private key. And these keys are generated by the client, and they're scoped to an effective top-level domain +1. So you get new keys for basically, not for every different server, but for every sort of higher-level top domain. And then there's a support for federated use cases, cross-domain type of use cases via this thing called the referred token binding, as opposed to what's called the provided token binding. A lot of the terminology is, I think, a little bit confusing in the world, but the idea of provided and referred is important, in that provided is about the key that I use, that the client uses directly with the site, and referred is about referring to a key that's used with a different site when communicating with an original site. So that's a quick overview. We'll get into the details a little bit more as we go on. So it all starts out in TLS, and in TLS they were kind enough to leave some extension points in the exchange of messages. So when the client initiates the TLS connection, the handshake, there's a client hello, there's some other messages that go back, there's a server hello that it responds back. And there's extension points in both of these that allow for additional extensions to be negotiated during the handshake. So there's, which we'll see how this is used in token binding here in a minute. And basically it goes like this. When the client initiates the client hello message, it does its normal thing, but it also includes a token binding extension, which happens to be keyed off the number 24 here. It's just a single byte that represents that, so it's relatively compact, but it's conveying to the server, it's saying, hey, I want to do this, I want to try to do token binding. And it's part of the TLS handshake. In addition, that extension contains the version, which once it becomes real will be version 1.0, just 2 more bytes there. And it also includes a key parameters list, which is a list of bytes representing basically the key types and signing algorithms that this client says it can support. And there's 3 defined right now. There's 2 RSA variants and elliptic curve ECDSA 256-bit variant. And they're just different signing algorithms and different key types, but it allows for there to be some algorithm negotiation between the 2 systems. And so the client lists the ones that it's willing to do, the types of keys and signing that it can support. The server gets this message, assuming it supports this stuff, and also if it has extended master secret implemented and secure renegotiation extension, a few things that are necessary here. Assuming all that's good, the server responds with its server hello, a token binding extension using the same value, a token binding version. Again, it's the same value, just indicating that we've negotiated the same version. And a key parameters list, but in this case, it's a list just to reuse the same structure, and the server's only allowed to respond with a list of one item, and that is the key type and signing algorithm that we're going to use together. So in this case, the server's saying, yes, this is great, we'll do token binding, let's do it, and I've selected the ECDSA P256 curve to do the signing, so let's use that together, and the client then knows to generate a key of that type if it doesn't already have one, and use that to do the signing. Assuming negotiation is successful at the TLS layer, this is what happens on every single HTTP request with that server going forward, or at least during the course of that TLS session. This new header, sec-token-binding is sent, and that just contains an encoded token binding message, and that message itself is just binary, base64 URL encoded, and inside of it, there's one or more token bindings. Typically, it's only one. There's a case where you're doing the referred cross-domain stuff where there's two, but normally there's only one here, and each of those bindings contains a type indicating whether it's provided or referred. There's the token binding ID, which is a really confusing name, but effectively the ID is the public key that this client's going to use with the server. And then there's a signature over the type, the key type, and the EKM, the EKM being that unique identifier for the TLS session. And there's some area for extensions that haven't been used yet, but maybe will be in the future. And ultimately, by verifying this, what the server gets, what the client does, is proves possession of the private key with respect to that TLS connection. So that message couldn't be reused, couldn't be validated on any other TLS connection without re-signing the TLS EKM and proving possession of the key. And so if the message is somehow stolen, this couldn't be played against a different channel. What I'm saying, basically it proves possession of the key with respect to that TLS connection, so these messages won't validate anywhere else. These keys are generated by the client, so there's no key distribution involved. The client generates the keys on demand as needed, and the keys are long-lived and span multiple TLS sessions. So even though we're signing a bit of the TLS session, if that session expires, if you go home, close up your laptop, go home and reopen it and start working again, you have a new TLS session, but the same key is used to sign the EKM from that. And so you have this sort of long-lived, persistent key to which things can be bound to that don't change over time. The most straightforward application of token binding is to bind cookies, particularly session cookies, to the token binding key. And once all the other stuff is done, this is pretty straightforward to do. The server associates the token binding ID, which again is the public key basically, with the cookie on its initial issuance of it, and then checks it on subsequent use. And this prevents the cookie from being used by any party that doesn't have the associated key. If the cookie is exfiltrated or leaked somehow, it can't be used without demonstrating the proof of the token binding key to which the cookie is actually bound to. One nice thing about this is it augments existing authentication and session management mechanisms. Token binding itself is not an authentication mechanism, and it can be layered on top of existing session management mechanisms that are making use of cookies for sessions and add additional security to that when, in fact, it's been negotiated. But if it's not negotiated, it's not there, it can fall back to the normal sort of functionality that we have today. So it's sort of an opt-in or opportunistic increase in security, but things still work when not present. And this can all be transparent to users. It's being implemented in browsers already. Once the browsers and the servers are implemented, we can increase security around our session tokens and our cookies in a way that average users, even sophisticated users, don't even know is happening. So it's opportunistic and transparent to users, which I think will help over time in adoption. And this also means that deployment can be phased in. There doesn't have to be one big bang moment or a server and a client that turn it on together to make it work. Different systems can turn it on over time. As implementations and deployments grow, more and more systems can take advantage of it, but it doesn't have to be all done at once. It can be phased in over time, which should allow for deployments and adoption to work without needing that sort of one big moment, which oftentimes those sort of events are hindrance to adoption. Some people, when they see this, get concerned that this generated key that's sent on every request is going to be some sort of super tracking mechanism or some sort of super cookie that will facilitate advertising or Big Brother or whatever. But token binding is not that. It's not a super cookie. It's not a Big Brother mechanism. What happens, and I mentioned this before, but a client generates a unique key per effective top-level domain plus one, sometimes also called ETLD plus one. And that's the effective sort of super higher level domain. So for example, like example.com, www.example.com, and etc.example.com will all receive the same token binding key from the same client. However, a new key will be generated and used with example.org, because it's a different top-level domain, plus one, as well as example.co.uk. In that case, that whole piece is the ETLD01 because of the co.uk. So the same scoping rules and privacy implications apply as do cookies. They're not broadened here. Any tracking you can already do by setting cookies is possible with token binding. That is to say, no additional tracking is possible through token binding. All that it's doing is giving a facility to strengthen those cookies, bind them to a key. It's not enabling any additional tracking functionality. It's not to say what we have with cookies is right. It's not necessarily to say to defend it, but it's the way of the world. It's the state of things, and this doesn't make it any worse. So what if we want to do cross-domain single sign-on federation that takes advantage of this functionality? There's an HTTP response header defined in the specification, and what it does is it tells the browser that on redirect from one site to another, that it should reveal the token binding ID, again, that's the key with the weird terminology, that it uses between itself and the relying party. It should reveal that in addition to the one that it normally uses with the identity provider when it makes that request to the identity provider. The flow looks a little bit like it would here, just in the abstract. The relying party redirects, it includes this include, referred, token, binding, ID, true, very verbose, but that's what and it does exactly what it says, include it. And the browser sees that, and the subsequent request it makes to the IDP includes the sec token binding header, but you can see it's a little bit bigger, or actually about twice as big, and that's because this particular one contains two token bindings, proving possession of two keys. One, the key that would normally use with the identity provider, that provided token binding ID, and that the identity provider can use to do whatever it's doing, bind its own session cookies or whatever it needs to do. But it's also then including a token binding ID, a key that's typically used between the browser and the relying party, and this is the key to which the identity provider can bind the SSO token, the SAML token, or more likely the OpenID Connect ID token, such that it's when it's delivered back to the relying party, it can verify that it was in fact bound to the keys on the client, which the client can then prove possession of use over the TLS connection back to the relying party, basically making it so it's impossible, without stealing the underlying keys, to steal that token, the SSO token, and use it by anybody else. So just a quick look at the specification landscape, because we like to break things up and make it complicated. There's a base set of specifications that are in the IETF working group for token binding. There's the TLS extension for token binding protocol negotiation. This is what defines the TLS extension and handshake negotiation. There's the token binding protocol, which is kind of, I don't think of it as protocol, it's a weird name for it, but basically it defines the message format, the binary message format for what these messages look like. And then token binding over HTTP defines the header itself and how it's encoded, as well as the response header, and basically how it applies to HTTP and HTTPS itself. Then in OpenID Connect and the OpenID Foundation, there's an OpenID Connect token-bound authentication, which is actually a relatively simple standard that talks about how token binding can be applied and used to secure OpenID Connect single sign-on. In OAuth, there's OAuth 2 token binding, which is less simple, but nonetheless interesting. And there's some stuff being worked on that's meant to ease sort of deployment problems. As mentioned in the previous session, I think Justin mentioned that almost everywhere, TLS is terminated somewhere other than the application. And that can be really problematic for a spec like token binding, where you need a lot of the information from the TLS layer at the application. So this HTTPS token binding with TLS terminating reverse proxies, it's a bit of a mouthful, but basically it helps define how systems can work and still do token binding in a way that's actually functional when they're in a deployment model where TLS is terminated somewhere other than the application. We'll look at each of these in a little bit more detail. So there's the base 3 specifications, negotiation protocol and token binding for HTTP. And basically those describe and define what I've described in the first part of this presentation. All 3 of those drafts are in the final throes of the IETF process, which is getting close to RFC status. I put the little asterisk on close there because I think I've said this as a few times. And time runs a little bit different in the IETF, so things are a bit slow. But I think this might be the last time I stand up and have to present and say it's close. They really are. They're at the very final stages of the process, and they should be RFCs, I think, sometime this summer. I hope. There's draft support for some of this stuff already in Google Chrome and Microsoft Edge and Internet Explorer in the .NET framework. Google servers have been running it globally for over a year now. There's open source work available for token binding implementations in OpenSSL, in Apache as a module, in Nginx, and in Java. So despite it being in draft, it's not even official standard yet. There's already work and availability on some implementations. There's OpenID Connect, token-bound authentication. This is the draft that talks about how to apply token binding to bind the ID token. And it's pretty straightforward, similar to the little diagram of the referred token binding I showed earlier. And really what it does is utilize that include referred token binding ID header that the RP can use to instruct the user agent, the browser, to send the referred token binding over to the IDP, which in turn, the IDP is able to take that referred key and bind the ID token that it issues to that referred binding, and then send it back. Thank you. And in turn, then that allows it to bind basically that ID token to the token binding key used between the browser and the RP. And it's a little hard to see, but here's the unencoded claims of an ID token that has the confirmation method that is used to include this information. So what happens is there's a CNF, which is short for confirmation claim, inside the JOT, and inside that there's a TBH claim, or TBH member, that is the hash of the public key of the token binding ID key. And so that's how the ID token itself is bound to the key that's used by the browser. And in turn, in validating the token, in addition to the normal stuff that's done to validate an ID token, the relying party of the client then also needs to check that the key presented at the token binding layer matches the key that's bound inside of this ID token. There's also token binding for OAuth. And there's quite a bit more involved here because there's a lot of different credentials and tokens flowing around in OAuth. But the main use case probably is binding of access tokens via the referred token binding, very similar. It uses the same confirmation method if it's a JOT-based access token. And also the confirmation is then defined to be used in introspection. So if they're reference style tokens, are using introspection to find out meta information about the token. The same data structure, that CNF, with an embedded TBH that includes the hash of the key is communicated either way. There's also advice for how to bind refresh tokens. There's some additional data around client registration, server metadata to convey to the other parties what aspects of this stuff is supported. There's a bunch of other stuff, including some PXE variants to do token binding, and some additional stuff around JWT authorization grants and client authentication that allows those credentials to be bound as well. This is an IETF spec. It's in working group draft, which means it's sort of being worked on by the working group, but it's not yet RFC. And while I don't expect any major changes coming along, you never know. And I do anticipate, based on the complexity of it and the need for underlying functionality to be in place, that this will be in draft for a fairly long time. The little diagram up there, it's hard to see, but this shows the binding of an access token just through a flow where a request is made with a refresh token to the authorization server's token endpoint. And basically it's a normal looking request, except there's the sec token binding ID header there that includes both the provided and the referred token binding. The authorization server then binds that access token to the referred token binding, shown there in the middle right yellow portion by that confirmation claim, including the hash of it. And then when the client presents that token to a resource server, a protected resource or an API, it just includes it like it normally would as an authorization header. but it also has proven possession of the corresponding token binding key through the sec token binding header, and that binds the two together and ensures, gives the resource or the API some assurance that the token is actually being presented by the client to whom it was issued. There's this piece about deploying behind TLS terminating reverse proxies, and really all this does is define a few additional HTTP headers that are to be used directly between the reverse proxy and the backend application server that allow the reverse proxy to negotiate and do token binding with the client itself. From the client's perspective, it looks exactly the same, but then the reverse proxy validates the token binding message, extracts the validated, checks the signature, and then pulls out the key and re-encodes the key in a header and passes that along to the backend. And the backend then doesn't need to do any of the signature validation, doesn't need to be aware of the TLS connection up front, but it still has access to the token binding ID, the token binding key the client has proven possession of, and it can bind or verify tokens against that. So hopefully this will help ease adoption in cases, the many cases that exist where TLS is terminated somewhere else in the application. And with that, I got the 1 minute mark, and I am done. So thank you very much for listening to my spiel. And
And you're right, there is really no time for questions. But thank you again, Brian. That was fantastic.
Thank you.
Appreciate it, everybody.
Lunchtime.
Lunchtime. Thanks to the people in the back.